Okay guys, so before break, well, I don't guess we can call this a break. Before we were out of school forever, we started notes on 3-1 to 3-3, but since we're out, I wanted to go ahead and use this time to break it back down into 3 sections, and so maybe you'll be able to understand it a little better. Okay, if you hear Campbell, I'm sorry, she's in the background, but if you want to download the notes, go ahead and do so. You don't have to. You can just write this down, just listen, whatever. So, identifying characteristics of quadratic functions is what we're looking at. And it says that a quadratic function is a nonlinear function that can be written in standard form. And we know standard form is y equals ax squared plus bx plus c, where a cannot equal 0. And the U-shaped graph of a quadratic function, remember, is called a parabola. Okay, so it says, in this lesson, we'll graph quadratic functions where b and c equal 0. So it's just, the function is just like ax squared, or like 2x squared, 4x squared, something like that. And that is read as f of x, which we should remember. And the notation for f of x is another name for y. So they mean the same thing. A parent function, remember, is the simplest function in a family of functions. And the parent function of a quadratic is just f of x equals x squared. And it says that the graphs of all other quadratic functions are transformations of the graph of the parent function. Okay, so remember when we graphed f of x equals x squared, that's that one we graph every time. That's our parent function. When we look at domain, it says the set of all possible x values in the function. That's what the domain is. And it's found by reading the graph from left to right. So remember, we read the same direction we read books. And the range is the set of all possible y values in the function. And the range is found by reading the graph from bottom to top. Okay, so if we look at this graph here, our domain, remember, it's all real numbers. We can write it with that r or from negative infinity to positive infinity. So either way you want to write it is fine with me. The range, that's where we look at the y values and we read it from bottom to top. So here we are, the first y value that we use in this graph looks like it's -4. So our range is when y is greater than or equal to -4. So remember, if it opens up, these values are all greater than or equal to -4. If it were to open down, they'd be less than -4. So that's why we have that sign there. Okay, it says a reflection, that is when we flip the graph of the function over the x-axis. So it would start like this graph right here, opening up, and when we flip it or reflect it, it then opens down. Sorry, Campbell just grabbed my headphones. I don't know if you could hear that. But when we flip it, it opens down. Okay, next page. And this will have to be broken up into a couple different videos, so this will be part 1. Okay, the vertex. Remember, the vertex is the lowest point on a parabola that opens up, or the highest point on a parabola that opens down. So if you can barely see these, but this one opens up. This lowest point down here is your vertex, and this one opens down to your vertex up here. Remember, we also talked about max values and min values, so those are the same right there. This is the vertex of a graph, f of x equals x squared is 0, 0. So that parent function always starts at 0, 0. Okay, axis of symmetry is what is next. Let's see. Okay, so the axis of symmetry here, that's the vertical line that divides the parabola into 2 symmetric parts, so it makes it equal. And it says the axis of symmetry passes through the vertex. So it's that dotted line that we draw right through the center of the parabola. And it says to find out whether the function is increasing or decreasing, we read the graph or the parabola from left to right. And that's what we'll do down here. So example 1, it says to use the graph, identify characteristics such as vertex, axis of symmetry, behavior of the graph, where it's increasing and decreasing, and the domain and range. So our vertex, that's our vertex right there at that center point, the lowest point. We can see that ordered pair is -1, 3. So that's our vertex. We want the axis of symmetry next. Remember, that's our x. We just say x equals, and it's this line right here. It's also the same number that we use in our vertex. So x equals -1. The domain, remember, is always all real numbers. Our range, we're looking at the y values. So bottom to top here, this is the first y value that it uses. Okay, and that is 3. So these numbers here are going to be greater than 3. So we say y is greater than or equal to 3. And I would prefer you to use this notation because sometimes you'll mess this one up. But you can write it either way. Okay, and then it says increasing and decreasing. We want to use x values for this. So if we read our graph left to right, starting here it's decreasing. So that's decreasing, and it turns at the vertex and it starts to increase. So how we write this, we use x values, and we know we're going to use -1. So when it increases, these values are greater than -1. So x is greater than -1. These values over here, when it decreases, these are less than -1 because -2, -4, -7, all of those are less than -1. So it's x is less than -1. Okay. All right, so I want you to pause the video and try these on your own. If you're doing them on the notes, even if you're not, I would like you to pause the video and just try them written on paper or whatever. But do that for me. Okay, so hopefully you paused the video and tried them. On this one, the vertex, if we look right here, it's 2, -3. Our axis of symmetry is x equals 2. Domain's always all real numbers. Our range, we start with the y value. So you can always look at this y value right here of your vertex. And so it's going to be y with -3, and it's opening up, so all of these numbers are greater than -3. So y is greater than or equal to -3. Now we've got to do increasing and decreasing. So from left to right, it starts out decreasing, and then it increases on this side. So remember, we use x values, so we're going to use this 2. It's decreasing when x is less than 2, and it increases when x is greater than 2. Okay, so number 2 over here, our vertex for this one's -3, 7. Axis of symmetry is -3. Domain's always all real numbers. Range, okay, still using this y value, 7. And then it opens down, so all of these numbers are less than 7. So y is less than or equal to 7. It starts out this time from left to right, it's increasing first. And then it turns and decreases. So it's decreasing. Remember, we use x values, and our x value is -3. It decreases when x is greater than -3 and increases when it's less than -3. Hopefully you got those correct. All right, so now we're going to start looking at the transformations that occur. So we have vertical stretches, and that makes the parent function thinner or more narrow, however you want to say that. In a vertical stretch, the coefficient, which is the a, it's greater than 1. So it's either going to be like 1/2, 2, 7, anything like that. A vertical shrink, so we have stretches and shrinks. The vertical shrink makes the parent function fatter or wider, however you want to say that. It's also known, and this should say horizontal, it's also known as a horizontal stretch, but we don't need to memorize that. We just need to memorize vertical stretch and vertical shrink. Okay, in a vertical shrink, the coefficient is between 0 and 1. So in a vertical shrink, that means it's going to be a fraction. So a stretch is greater than 1, and I think I accidentally said like 1/2 or something earlier. So the vertical stretch is greater than 1. So 1, it would be like 1.5 or 3 halves. It can still be a fraction, but it'd have to be improper. So anything greater than 1 is a stretch. And Campbell's singing. Anything between 0 and 1, whether it's a decimal or a fraction, that's going to be a shrink. All right, next page. Okay, so example 2, graphing y equals ax squared when a is greater than 0. So we're going to graph 2x squared is what we're going to graph. So we make our table of values. Remember, we always graph our parent function first. So if you have your calculator on your tablet or one on the line somewhere, you can fill it out with this. Or you can just plug in these numbers. You do -2 squared, that's 4. -1 squared is 1, and so on. So remember, this is the graph we always do. We always put this on our thing. Alright, so now we want to graph 2x squared. So we're still going to use those same x values, and you can plug them in if you need to, or use your calculator. And it will give us all of these numbers. So 82028. Okay, step 2 is to plot the ordered pairs. So we're going to plot the ordered pairs for both graphs and draw a smooth curve through the points. So this is what our graph should look like. My pink graph is our parent function f of x. And my blue graph is our new function g of x, which is this one, the 2x squared. So once we've done that, it says that both graphs, we can see that they both open up. They have the same vertex, which is at 0, 0, and they have the same axis of symmetry. That axis of symmetry is x equals 0 because it's going straight through the center of them. And it says the graph of G is it going to be wider or narrower than the graph of F? And the correct answer to that is narrower or thinner, however, than the graph of F. So since it's thinner, this is going to be, it says the graph of G is a vertical stretch by a factor of 2 of the graph of F. So whatever number is out here, we can look at that and tell that that's a vertical stretch because it's greater than 1. Okay, so pause this video and try this, and we will pick up here on part 2. Okay, actually I had enough time on here to go ahead and finish this page with you on this video, and then part 2 we'll start the next page. So you should have paused the video and done this on your own. If you did, these are the x or the y values that you should come up with. And I'm pretty sure that we've done this example before. But when you go to graph both things, remember the pink function I graphed, that's our parent function. This function, our new one, is g of x. And if you notice, it's much thinner than f of x. So we know since it's thinner, it's going to be a vertical stretch. Remember, if you grab the ends and pull them, it gets skinnier. So that's going to be a vertical stretch, and we can look at this number right here to tell us that it's by a factor of 5. So you can say that the graph of G is a vertical stretch by a factor of 5 of the graph of F. And that's all you need to know. All right. I'll finish this in part 2.